guys, and welcome back. Now we're going to have a look at some applications of connecting our components in parallel. First one we're going to have a look at is Christmas lights, but before we do the parallel version of this, let's just have a look at how or what would happen when you connect them in series, and then we'll see why parallel is in fact better for our Christmas lights. So the first thing we're going to have a look at here is just get a different color. Let's go a nice purple. Now if we have a look here, these are connected in series. Just going to try and follow this line as best I can. So all of those electrons are going to flow through each of these 10 light bulbs like that. They have to go through every single one. Now if each of these light bulbs has a resistance, because light bulbs are made up of these little wound filaments in there, and that's what gives off light when electrons go through them. But if each one of these is worth 10 ohms, and we've got 10 of them, we've got a total resistance, RT, of 100 ohms. If there's 10 volts over here, 10 volts divided by 100 ohms. Can pull that up on the calculator just to make sure we're doing this correct. 10 volts divided by 100 should be 100 milliamps. There it is. 100 milliamps of current. So those lights would be glowing a certain brightness. But let's say that we wanted to extend this. We wanted to have more than 10 light bulbs. Let's say we wanted 11 or 12 or 13 or 14 or 15 or whatever it is. If we were to go to 15, what would the total resistance be now? Let's have a look. Total resistance would now be 150 because we've added an extra 5 resistors to our circuit. 150 ohms, what's the current going to be? Well, it's going to be 10 volts divided by, because we've got 15 resistors, so 150 ohms, or I should say 15 light bulbs, which have a resistance of 10 ohms each. 10 volts divided by 150 ohm, it's now gone down to 66.67. 66.67 milliamps, so we've got less current. If there's less current in the circuit, the light bulbs are not as bright as they were before. So just by adding more light bulbs, you're actually causing them all to be not as bright as before. So that's a bit of a problem. What's another problem? Well, let's say that these light bulbs are on, they're on our Christmas tree, they're shining and everything, and then all of a sudden, one of them blows. So that light bulb has the little filament inside, has vaporized, it's blown, it's an open circuit, just like I've shown here. That has actually cut all current in that whole circuit. So what's going to happen to every single one of those other light bulbs? Well, they're all going to turn off. So just by one light bulb out of the 10 blowing, we've actually caused every single light bulb to turn off. So now you're looking at the Christmas tree going, that was on just a second ago. You then go up, do you have any idea which one is blown? Well, you don't, because all of them have turned off now. You've got to individually take out one, test it, take out the other one, test it until you find which one is blown. You replace the one that was blown, put it back in the circuit, and they all glow again. Unless, of course, 2 of them were to blow at the same time. So it's a little bit annoying to have to do that. So not so good. But what about in parallel? So in parallel, what we're doing is we get each one of these 10 light bulbs over here, and they directly connect to the power supply like this. So they each get their own amount of current going through there. The good thing with this one, even if you were to add an extra light bulb, if you were to go to 15 light bulbs, every single other light bulb is still as bright as it was before, because every single one is directly connected to the power supply. Now, there is one thing that happens with this. If you were to connect up, in fact, let's look at the circuit simulator. I've actually built it in there. So there's all our light bulbs. 10 volts coming in here. Here's all our light bulbs. They're on because they're yellow. If we have a look at the current through each, that's a 10 volt power supply, that's a 10 ohm light bulb, we get 1 amp. 1 amp, 1 amp, 1 amp. Each one of these gets 1 amp. So we get a total of about 10 amps. Now this particular program here, it does some extra calculations in there to account for the resistance in all of these wires. So we don't need to worry about that, but it's actually giving us 10.01 amps, but let's just round it off to 10. Now let's say that we're sitting there, we're watching the Christmas tree, the lights are on, it's nice and bright, and then this one here was to blow. It's gone. Well, every single one of these other ones is still on. That's because this one had no effect on those other ones, because they're each individually connected to the 10 volt power supply. because they're in parallel. But what did that change? Well, it caused our total current to go from 10 just down to 9. We put that light bulb back in, we're back to 10 amps. So when you put things in parallel, they're all directly connected to each other and directly connected to the power supply. If just one light bulb was to blow, it doesn't have any effect on the rest. The only thing it has an effect on is the total current coming from the power supply. So how easy is it going to be for you to figure out which light bulb to fix? Well, it's going to be dead easy because the only light bulb that is turned off is the only one you need to fix. It doesn't have an effect on all the other ones. Let's put it back in. What if we wanted to add an extra light bulb? How hard is that? Well, let's get that one there, put that in there, connect that to there, connect that to there. So this one is now on. Does it affect the other ones at all? No, it doesn't. We still have 1 amp flowing through these because by connecting that one, we did not in any way change how the other ones were connected. The only thing that it does change is we've now got 11 amps instead of 10. So in parallel, the only thing that we're actually affecting is we're getting more total current flow in the circuit. And that's it. Now, so the other one I wanted to show you guys was a power board. So this particular power board is an Australian power board. Surprise, surprise, I'm from Australia, hence my Australian accent. But these particular power boards, they connect into the wall, and then from there you get 4 connections with which to use from there. So it effectively extends 1 connection in the wall to 4. Now we haven't done any AC stuff. We've only been doing DC, but all that's happening is all of these connections are all connected together, and they all go to the same connection on the wall over here. Then we get this connection here, and these are all connected together, and then from there that goes to the wall over here, and then finally we've got this one down here that goes all together, and then from there that goes to the wall over there. So all in parallel. Now the cool thing with this is I can come along, plug my laptop in, and the laptop might go down into here, and then I might get a light. So when I'm doing some filming stuff like this, I need to plug in a light so you can actually see me, so that could plug into there as well, and then I might get something else like a power supply for when I'm doing those breadboard circuits. That might go into there, and then I can have another thing, like I might be charging my phone or something that goes in there as well. Because they're connected in parallel, they all have a direct connection straight to that power supply wall connection. So just to put that into something that you might understand a little bit better, we can simulate it with this thing. So we've got 1, 2, 3, 4, and nothing is connected there at the moment. Therefore, there is no current flowing in the circuit. But if I was to come along, and then let's just pretend this resistor is my laptop, I connect that in, and that has a direct connection straight to the power supply. And there's 10 milliamps flowing just in this case, if that was 1K. Okay, then let's say I come along and then I want to plug in my phone. I want to charge my phone. So I could plug it in there or there or there, it doesn't matter. Plug it in, wherever I plug it in, it has a direct connection straight to the 10 volt, power supply. There's 10 milliamps going through there. What does that change about this one? It doesn't change anything about that one. That one is still 1K. It's still got a direct connection to the 10 volt power supply, so it's still got its 10 milliamps. If I get rid of that one, nothing changes about that one. It's all the same. But what does it do to the total current? Well, total current is now 20 milliamps. If I disconnect that, my phone's fully charged, then I'm back to 10. If my laptop is fully charged and I want to unplug that, just disconnect it. Maybe I want to come and connect up a light bulb, so I connect the light there. Does that change anything about these other two? No, it does not. It just changes the amount of total current we get. And then I might want to plug in something else like, I can't remember, a television. So a television can plug in there. It doesn't change anything about these other three because they still have a direct connection to the power supply. The only thing it does change is now that there's more total current coming out. And I can unplug any of these whenever I want, and everything else still works just the same. It just means there's less current now. So that's the cool thing about connecting things in parallel. Now, of course, as we go through later lectures, we'll be seeing parallel circuits again, and with other components as well. But this is just a bit of an introduction, connecting resistors in parallel.